Hey, honors pre-calc, welcome to lesson 3.5, exponential and logarithmic models. We've made it to our last lesson in unit 3 on exponential and logarithmic functions. And in this lesson, we will be kind of just piecing everything together and applying it to applications in the real world, right? So one thing we will do today is to use exponential growth and decay to model real world scenarios. The essential question today is how can exponential and logarithmic equations be used to model real-world scenarios? And here's an example of something you will be able to do. Believe it or not, the spread of a virus can be modeled using logarithmic and exponential equations. So if this is a model where y is the total number infected after t days, we can answer a question like after how many days will 2,000 people be infected? So we'll answer that question a little while later. But with that being said, let's head over to the notes. All right, so here are our notes for 3.5. You can see here's our general model for growth and for decay using an exponential function. The A and the B are placeholders for constants that would be plugged in here. The X is the variable, so that'll stay X. The Y is a variable, it'll stay Y. And E, as we know, is our a number that we've been using a lot, right? That doesn't have some random value plugged in. E represents the same thing every time that we use it, okay? We're also gonna be seeing a few other models in this lesson. We're gonna be looking at something called the Gaussian model, which we'll explain when we get there. We've got logistic growth and logarithmic models. But we're going to start out with exponential growth. So that's this first equation up here. Also, I wanted to mention that you do not have to memorize all of these formulas. Anytime that you have an application question that would require the use of some of these formulas, that formula will be given, okay? So let's take a look at example 1. Estimates of the amounts in billions of dollars of US online advertising spending from 2007 to 2011 are shown in the table below. And you can see I already labeled because I forgot when I was typing this question to say that 2007 represented a t of 7. So for the years, we're going to be using 7, 8, 9, 10, and 11 as the t value that we plug in. An exponential growth model that approximates this data is given by this formula here, where S is the amount of spending. Using this model, estimate when the amount of spending will reach $40 billion. All right, so you can see that the amount of spending is clearly increasing over time. And you can see also that it's increasing quicker over time, which lends itself to an exponential growth model. So if this fits the data, we're supposed to estimate when the amount of spending will reach $40 billion. So I'm going to start with that formula and write it down. E to the 0.1022t. And S is the amount of spending in billions of dollars. So we're going to be plugging in 40 for S. Okay, and now we're going to try to solve this. So the first thing that we're going to do to isolate the t, to get the t by itself, we've got to get rid of this 10.33. So I'm going to divide both sides by 10.33. And then to get this e out of here, we're going to have to take the natural log of both sides. That's something we learned in previous lesson this unit. And for now, I'm just going to leave it as 40 over 10.33. But we will, in the end, use the answer to approximate. So our next step is going to just have natural log of 40 over 10.33 equals 0.1022t, right? Because the natural log e cancels out. And now we can divide by 0.1022. And we've solved for t. Now that doesn't really answer the question. Estimate when the amount of spending will reach $40 billion. Okay, so that's what this represents, but that's kind of a mess. So what I would do is type this expression into a calculator, and we will get that t is approximately 13.2. So that's what the decimal approximation is of this expression. And if we look at our years, 13.2 is going to be during the year 2013. So that is about approximately the year 2013. And let's see if that makes sense. 40 billion, yeah, that's a little bit more than 32. And you can see it's increasing quicker over time. So it makes sense that by 2013, in 2 more years, it will get all the way to 40 billion. All right, example 2. Modeling population growth. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? Okay, so for this question, we're gonna be using the exponential growth equation from the top of the notes sheet. And I'm gonna tell you right now, that we're going to have 2 different variables. X, we're going to say, is our number of days, and Y is going to be our number of flies. And we're going to be using the exponential growth model. That's Y equals A e to the bx. We're looking for how many flies will there be after 5 days. So if we set up a chart of X and Y, what do we already know? We know that 2 days will be 100. We know 4 days will be 300. And what we're looking for is 5, right? So if we think about our model here, we have 2 different examples of an X and a Y that match up. And we have 2 different constants that we need to find, A and B. So what we can do here is set this up as a system of equations. So the first equation is going to be 100 equals A e to the 2b. And the second one is going to be 300 equals A e to the 4b. Okay, so let's talk about why that is. Remember the exponent was bx. I'm plugging in 2 for x, and I'm plugging in 4 for x. I still don't have the b. And the y is being replaced by the 100 and the 300. So now we have 2 equations and 2 unknowns. The unknowns are the A and the B. Remember, E is not a variable. E is a number that we already know the value of. And that value is 2.718, etc., right? That's a constant. It stays at E. We're trying to find the values of A and B. So let's do this using, our substitution method. So we're going to solve this equation for A, and then use that over here to find B. So here's what I mean, and follow along. This might take us a second. So I'm going to solve this for A. So I'm going to get, if I divide, I'll get 100 over e to the 2b equals A, right? So I'm going to take that and plug it in to this equation. So I'm going to get 300 equals, and now I have 100 over e to the 2b times e to the 4b. So I replaced the A, or substituted, right? That's the substitution method to solve a system of equations. We substituted in 100 over e to the 2b in place of A. Okay, so next step. Notice that we have an e to the 4b, which is really kind of like in the numerator here, and an e to the 2b in the denominator. Your properties of exponents will tell you that that means we can subtract these exponents and to get rid of the denominator. So we really have 300 equals 100 e to the 2b, right? Because 4b minus 2b is 2b. And what's next? So we can divide by 100 on both sides. 300 divided by 100 is going to be 3. And let's keep going to solve for b. So now we're going to take the natural log of both sides. That causes this to cancel out. So we get natural log of 3 equals 2b. And then I'm going to divide by 2. So I get natural log of 3 all over 2 equals b. And that is a good estimate there. So I'm going to use that and come back over here to the left equation to plug in for B so we can find A. So we get 100 over e to the 2 times natural log of 3 over 2. That says ln 3. It's a little hard because I wrote it so small, but I can't do much about that. So I'm going to leave that there. The 2 and the 2 are going to cancel, so we'll get 100 over e to the ln of 3 equals A. And what's next? E to the ln, that is lucky for us, that cancels out and leaves us with 100 over 3 for A. So we got A was 100 over 3, B was natural log of 3 all over 2. And so now we have a model, right? So if we go back to the original look of the model, I'm going to do this over here. We'll have y equals A, which was 100 over 3, e to the b, which is natural log of 3 over 2 times x. Okay, so that's our model for this situation. We could graph this and you would see it's an exponential growth to show the population over time, because the more flies there are, the faster they'll reproduce. And I am trying to figure out now, the last question is, how many flies will there be after 5 days? So 5 is an x value. We're going to plug that in for x and see what we get for y in our new model. So it'll look like that. Now that's all in the exponent. I already took the liberty of typing that into my calculator, so you don't have to watch me type that in. But if you calculate that all out, you'll get that there are approximately 520 flies after 5 days. Okay? So we just took systems of equations, which is a algebra 1/algebra 2 concept, and we just blasted it into our exponential and logarithmic unit to show that you can find, two unknown variables in a system of equations, even if there's exponents involved like this exponential equation. Okay? All right, so that was example 2. Let's keep going. Example 3 is all about carbon dating. So we're going to estimate the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is R equals 1 over 10 to the 13. Using the carbon dating model, R equals 1 over 10 to the 12, e to the negative t over 8,223. Okay, so t is going to be our number of years here. And we don't necessarily need to understand fully what this is really talking about, but basically there was a fossil, there's carbon-14 and carbon-12, there's a ratio here, we were given the ratio, so some scientist calculated this, and now we can use this carbon dating model to figure out what T is. So all we need to do to start is just plug that in for R. So we have 1 over 10 to the 13 equals 1 over 10 to the 12, e to the negative t over 8,223, just like that. And we're solving for t, so we're going to use the same system that we've been using. We got to get rid of this 1 over 10 to the 12th. So if you multiply by 10 to the 12th on this side to get rid of the divided over here, it'll be 10 to the 12 over 10 to the 13, which cancels out to 1 over 10. You can also just divide the fraction. But I would probably want to use calculator then, and I can figure this out pretty simply if I just think about what this is really talking about. So we got 1 over 10 equals e to the negative t over 8,223. Got to get that t isolated, so I'm going to take the natural log of both sides. That causes this to cancel, so I get natural log of 1/10 equals negative t over 8,223. So I'm going to multiply the other side by negative 8,223. And I'm going to type that into my calculator, negative 8,223 times the natural log of 1/10. And what I end up with is approximately 18,934 years. That's how old approximately our fossil is. There you go. Example 4, Gaussian models. In 2008, the SAT math scores for college-bound seniors roughly followed. Now that's actually interesting because I was a high school senior who graduated in 2008. So this is talking about my SAT math score. Interesting, interesting. I'll tell you, I was probably closer to the top of this interval. But anyway, it roughly followed the normal distribution given by this equation, where X is the SAT score for math. Estimate the average math SAT score. Okay, so first of all, if you have ever taken statistics or you're taking it right now, then you may know what a normal distribution looks like, a bell curve. It may show up in other math classes that you've taken as well. But basically what we're looking at here is if this is our x-axis, we've got a normal distribution, which looks like this. And that's telling us the number of people who scored each score. So we're going to be going from 200 to 800. What we're looking for is the average math score, which always happens right at the center of a normal distribution. So we need to figure out what that center value is. Notice that this is technically an exponential function because it has x in the exponent. And that is true for all normal distribution curves. You can graph them using exponential functions. In statistics, you don't necessarily see the actual formula here, at least from my memory of statistics. I don't remember doing that, but it's true, it is graphed that way. So anyway, if we take a look at our graphing calculator, I'm going to put y1 as this function that's listed here. So we've got that there. And we already know that x goes from 200 to 800. So I'm going to go to Window, change my x min and my x max to 200 and 800. I already typed that in. It used to be negative 10 and 10. After that, I go to Zoom, and I'm going to go to Zoom 0, Zoom Fit, because that will automatically make the graph into the right window of y values so that we can actually see the curve. And when I do that, this is what I get. Okay, so you can see we've got our normal distribution here. We're going from 200 to 800 on the x-axis. Those numbers are really close together, so we can't see any of the tick marks. And our y-axis isn't even showing up. So we're not, and that's because we started with an x of 200, not with an x of 0. So we don't see the y-axis. But anyway, all we need to do now is go to second trace maximum. And let's go a little bit to the left of the top and a little bit to the right of the top. And you can see the maximum is 514.99998, which we can round to 515. So that is x equals 515. And there's no units for an SAT score, that it just is the score. And if you take a look at the equation, you'll see that that 515 actually showed up in the exponent. So that's actually telling us the maximum in the equation. So that's good to know for future use. In a Gaussian model or normal distribution, the max usually shows up so that you can see it. And I'm also just going to write down so that I remember what I did in this question, that the average is the maximum value. Okay. There was a y value here. The y value is given as 0.0034. That's just telling us that that's the percent of people who scored that score. But we weren't asked for that. We were just asked for the average score. So that's what we got. Okay. All right. Example 5, logistic growth model. This one may hit a little close to home here, but This question has been in my notes for years because contagious viruses do follow this type of a model, a logistic growth model, so it's very applicable. On a college campus of 5,000 students, one student returns from a vacation with a contagious flu virus. The spread of the virus is modeled by this equation here, where t is greater than 0, where y is the total number infected after t days. The college will cancel classes when 40% or more of the students are ill. How many are infected after 5 days? Okay, so to answer that first question, t is the number of days, y is the number infected. So if we're going to figure out after 5 days, we're going to plug 5 in for t. So we're going to have y equals 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. And if you type that into your calculator, what you will find is that it is approximately 54 students who will be infected. And then letter B, after how many days will the college cancel classes? Okay, so this question gets a little trickier. So take a look up here. College will cancel classes when 40% or more of the students are ill. There's 5,000 students. So the first thing we need to do is figure out what is 40% of 5,000. And that's going to be 2,000. So we're looking specifically at 2,000 students here getting infected. So that is the y value, right? Y is the total infected. So we're going to have 2,000 equals, and we're going to leave t as t this time and try to solve for t. Okay, so that's what we have first. And I'm going to choose to multiply this whole denominator to the other side because I don't want that t to be in the denominator. So I'm going to have 2,000 times 1 plus 4,999 e to the negative 0.8 t equals 5,000. Then I'm going to divide by the 2,000. And I end up with 5 over 2. Because it was 5,000 divided by 2,000, which just reduces to 5 over 2. Then I'm going to subtract 1. Which gives me 1.5. I just switched from fraction to decimal, but you can, yeah, that's what I did. Doesn't matter. 1.5 or 3 halves. Then I'm going to divide by 4,999. I get e to the negative 0.8 t equals, I'm just going to leave that as 1.5 over 4,999. Okay, now we take the natural log of each side. And I'm just going to kind of cancel that out as I go to save some space here. So I'm going to get negative 0.8 t equals the natural log of 1.5 over 4,999. So I took the natural log of this side, it canceled with the e to leave me with that exponent. Over here, the natural log stays. And next, I'm going to divide by the negative 0.8. So in the end, we need to know how many days. So this isn't going to answer our question. We're going to want to type this into our calculator to get an approximation. So I'm going to type in natural log of 1.5 over 4,999. And then I'm going to divide that answer by negative 0.8. And when I do that, I end up with 10.14 days. Okay. Last example, example 6, logarithmic models. On a Richter scale, the magnitude R of an earthquake of intensity I is given by R equals log of I over I naught. If you take in physics, if there's an I with a sub-zero, it's usually referred to, or any variable with a sub-zero is usually referred to as I naught or something naught. Where I naught equals 1 is the minimum intensity used for comparison. Find the intensities per unit of area for the following earthquakes. Intensity is a measure of the wave energy of an earthquake. Interesting. Okay. There's all sorts of different applications for logarithmic and exponential equations, as you can see throughout this whole lesson. Letter A, Nevada in 2008 had a magnitude R equals 6.0. So if we use this equation up here, we're going to have 6.0 equals log of I over I naught, where we're going to use that as a 1. So it's really just log of I. So to solve this, to get rid of this logarithm so we can find I, we're going to do 10 to the 6 equals 10 to the log of I. That cancels up here, and we get 10 to the 6 equals I. And that's the answer, right? We found the intensity, and that's per unit of area. And so if we wanted to write that out, I would be approximately, well, pretty much exactly 1 million. In letter B, we have 7.9 equals log of I. So 10 to the 7.9 equals 10 to the log of I. So I is approximately, we do 10 to the 7.9, and this time it's going to be 79,432,823.47. A little bit more intense than the previous earthquake, right? Okay, so that is that. Very nice. Hope that all makes sense. That's the end of the lesson. So now you've got a practice worksheet to look at. I'm going to show you this real quick just because there are some questions on here that don't line up quite exactly with the notes. In the first question here, we have some data provided and then these graphs. So take a look. Notice that your calculator can give you like the best fit models for all different types of setups. So here's the data that's plotted from this table up here. And I used the calculator to model a linear regression, quadratic, and exponential. And each of these takes the model given and tries to fit it precisely to the data. Okay, so your job is going to be to try to answer these questions based off of those graphs. And then for 2 through 6, we had 2 data points. We ran a linear regression and an exponential regression. For questions 2 and 3, all you have to do is plug A and B into this linear equation, plug A and B into this exponential equation where the A and the B go. So that'll help you with those. If we flip over to the back, you will see that there's some data provided. You can figure these out if you kind of think this through hard enough. And then number 9, I think is a really interesting question. I think you'll be able to figure that one out as well if you put some effort into it. All right, so that is your assignment. Thank you very much for watching, and I hope you have a great rest of the day. Let me know if you have any questions.